So one of the pieces of data which is often found on NMR spectra is the integration. But integration is actually a mathematical function where you take an equation, usually a curve, and by integrating from one boundary to another, what it tells you is the area under that curve. So why does this apply to NMR? Because you look at NMR signals and you think, well, they look like perfectly sharp lines, but actually if you zoom in on an NMR spectrum on each of the individual peaks, you'll find that they're actually curves, and you can integrate the area under the curve to give you more data. So NMR processing programs will generally do this for us, and they will display this data one of two ways, either as numbers beneath the peaks down here, or as what we call the integrated trace, which are these red vertical lines that run through each signal. Now, the absolute values of either the integrated trace or the numbers, because they're essentially the same data, are not important, and often the leftmost peak is calibrated to 1 as standard. So what this data is telling us is the ratio of the areas under the curves here. So it's telling us that this has a ratio of 1 to 2 to 2 to 2 to 3 across this spectrum. And the ratio of the integrals, the ratio of the area under the curves, is equal to the ratio of nuclei which created those signals. So this doesn't give us any absolute data. This is not telling us that this signal over here was created by 1 proton and that this signal was created by 2. It's telling us that this signal was created by half as many protons as this signal, because the ratio is 1 to 2. So now we need to apply knowledge of the compound, or what we think the compound might be, to think what the most sensible ratio should be. So our options in this case, because we have a ratio of 1 to 2 to 2 to 2 to 3, our choices are compound based on that. So 1 to 2 to 2 to 2 to 3, 2 to 4 to 4 to 4 to 6, and so on and so forth. Now, do any of these ratios match what we're expecting the compound to be? Well, in this case, the compound is 4-ethyl benzaldehyde, and if we look at the proton chemical environment we're expecting in here, we're expecting 1 to 2 to 2 to 2 to 3. So this matches our initial integral ratio. So we know we've got a good idea that this is going to be a sensible structure. So if you're given a spectrum which doesn't have the numbers underneath down here, then all you need to do is look at the integrated trace, because it's the same data set. And what you need to do is measure the height of the integrated trace, so from here down to here, with a ruler. Again, the absolute values are meaningless, it's the ratio that's important. So the ratio of the height of this to the height of this should be the same. So it should be 1 to 2 to 2 to 2 to 3. So if you ever get a spectrum where you don't have the absolute data, get a ruler out, measure the heights of the integrated traces, and that should give you the same data.